Hello everyone, welcome back to the session. Let me welcome our next speaker, Andrew Richards. He's the CEO of Codeplay and he has gracefully consented to provide the special session on the oneAPI construction kit. And he'll be sharing his screen live for this session. And also participants, if you have any queries during the session, please feel free to post it in the Q&A tab and we will be addressing those questions at the end of the session. Thank you. Andrew, over to you.
Hello everyone. You weren't expecting me because I wasn't in the program for this time, so yes, it's switched over. I'm going to talk to you about the oneAPI construction kit, and this is about bringing oneAPI to your hardware quickly and easily. So this is particularly interesting to hardware designers or people who need to bring oneAPI to some new piece of hardware. I'm also going to talk a little bit about how oneAPI can map to hardware. So Codeplay, we are based in Edinburgh in Scotland, established in 2002. I'm the CEO of Codeplay. We grew to around 100 employees, but in 2022 we became a wholly owned subsidiary of Intel. So we still operate as Codeplay and we still expand the open ecosystem for heterogeneous computing. So the vision of Codeplay was always about making it possible to program all of the many different processors out there, particularly things that are going to give you extra performance. I was very interested in graphics processors in those early days, but we've done lots of other things, AI processors, DSPs, all sorts of things. And that's what this presentation is going to be about bringing that programmability to new hardware. And we are also have always been big collaborators in cutting edge research. We've always tried to stay at the cutting edge of new technologies in our field. And I'm going to talk a little bit about a couple of the projects that we've been involved in Europe, which are actually using the oneAPI construction kit to actually achieve programmability on some new hardware. Why is there so much demand for multiple architectures? We talk about data-centric computing because that's where you really have large amounts of processing, and a lot of that is now being driven by AI. But the reason we talk about data-centric computing is because when you're doing AI, there's lots of work that you have to do with large amounts of data. So some of it is these amazing neural network models, deep learning models that have achieved such incredible strides in artificial intelligence. But often they're not the only thing that you have to be able to run. So there's still a lot of it, high performance computing, scientific applications that runs on lots of data. But also we find that all the software for pre-processing and post-processing what goes into these generative AI models. So you're not just running the model, you're working the rest of it. And so that's why we use the term data-centric computing, is that you're processing huge amounts of data. And to do that, you need increasingly efficient performance. So you really need to drive down the power consumption, drive down the cost as much as possible. I know it's becoming very expensive, but it's important for us to still drive down that cost even further so that you can achieve huge amounts of processing with these new architectures. And we include CPUs and GPUs, FPGAs, and specialist AI accelerators in all of that, right? It doesn't really matter all that much to us if you're trying to get performance out of architectures. We're interested in enabling that for you. And yes, there are some differences between those architectures and how you enable that, but there are techniques for handling some of those differences at higher levels in the software stack. It's incredible that when Codeplay started, this idea of using GPUs for other things was pretty crazy. Now it's pretty commonplace. 48% of developers now say they target heterogeneous systems that use more than one kind of processor or core. So it's a really common thing now, having been totally nuts when we started Codeplay about a quarter of a century ago. Okay, so oneAPI, I'm sure you've been presented this a lot in this Dev Summit and will be presented it again, but this is my version of it. It's a unified programming model to simplify development across diverse architectures. So you have a unified and simplified language and libraries for expressing parallelism. We give you uncompromised native high-level language performance. So I should explain what this means, right, from a philosophy point of view. When people think, right, oneAPI and SYCL and things, they think, magic compiler, and so therefore it magically converts my code to be able to run fast on every architecture and Having worked in the field for 25 years, it's not possible. You're probably thinking that's not possible either. But what we can do is we can make this manageable by unifying things, by standardizing things, still giving you that ability to get native performance. So when you use oneAPI, you still have that ability to get that, really hard-coded, hand-coded native performance for one particular processor, but then manage it across a large application. So you're not having to rewrite everything to every new architecture. You're just going to go in and you're going to tune it. So we don't get in your way of getting the performance that you want to do through this native high-level language performance. But we do give you all of the standardization and all of the unified languages and stuff. So you're not doing silly stuff to be able to handle different. You're not having to deal with things that have got different names and different concepts between different processors for no reason. So we're making it manageable. We base it on C++ and the Kronos maintained SYCL open standard. That's because we found a lot of the developers using these kind of techniques were focused on C++. However, you'll find lots of people use things like Python and Fortran and Java and all sorts of other languages. And so that's why we enable people to work with other languages. So we're giving you a structure, is the way I see it. We're giving you a structure to enable you to manage developing software across all these different architectures. It's not magic. It's very well specified. It's very well engineered. It's something that you can rely on. And it's going to make your life a lot easier when developing across multiple models. And you'll see up here different ways that we break up those different names. So when people talk about GPUs and CPUs and FPGAs, it can be sometimes difficult to work out what that means from a software point of view, right? And so we break it down to things like scalar operations, vector operations, matrix operations, and spatial operations. I'm going to talk a little bit about that, but scalar operations is doing one operation at a time. Which is what CPUs are very good at, although CPUs also now have lots of vector operations. Vector operations is dealing with lots of data in once. And then you'll have matrix operations, which is being done a lot because there's a huge amount of computation in doing matrix operations in deep learning. And then spatial operations is about moving data around and data flow around the system, because it turns out that moving data around the system uses up much more power than actually doing the computations. This increased over the years. It kind of still amazes me. When I started programming, it took huge amounts of instructions and effort to do one floating point operation, whereas loading data from memory was like pretty much instant. And it's now the other way around, right? You can do huge numbers of floating point operations per memory operation. So what you want to be able to do is move data around the system. And SYCL and oneAPI are designed to allow that data flow optimization within the system. It's not always obvious how it's doing it, but it is doing it. You'll start to pick it up that it is actually a lot of what SYCL and oneAPI is doing is about handling that, moving data around the system in a spatial way, taking into account how far data has to go. And that's really important for performance in the modern world. If you've got a new processor architecture and you want to bring oneAPI to your processor architecture, that's where the oneAPI construction kit comes in. And the whole point of the oneAPI construction kit is to enable you to do lots of different innovations. So the oneAPI construction kit has to be very flexible to enable you to design the processor the way that you want to do it. But we make it very easy for you to do it. So I'm going to show you various options, and some of them may say, or you may think, oh, that doesn't map to my processor, but something like it does. These are all options, and it's a toolkit. So that's why it's called the oneAPI construction kit. It's got all of these different components within it to allow you to take different parts of your processor design and integrate it in. And then you add in your own customization to it. So remember that what we're doing with SYCL and oneAPI is we are going to be working in a heterogeneous system. So there is a CPU, and the CPU is probably going to be optimized for latency sensitive tasks. So turning things around very quickly, responding to something very quickly. And then the accelerator is probably going to be optimized for data intensive tasks, processing huge amounts of data. So it may take longer for it to turn around, a small bit of operations, but lots of operations happening at once that you get in this data-centric computing or AI, that the accelerator is likely to be good at that. So what we're going to do is when you look at your SYCL code, or if you look inside the libraries, you'll find that there's kernels, which we're going to move onto the accelerator, and those kernels are for doing the data-centric processing, and the host code is going to run on a CPU. We call it host, but it's the CPU is going to run the bits that are not the kernel. So we're going to move some of that code across to the accelerator, and the oneAPI construction kit is handling some of the movement of that code. And we're also going to have to handle the things like the data movement, right? Because you're going to have to move the data across with it and handle how to do that. Because the only way you get performance is through parallelism in these systems, then we're going to be able to have to do all of that at the same time. So the processing, the data movement, the CPU, the accelerator, they're all going to have to execute at exactly the same time. And the aim of this is once you've done this, you get the whole oneAPI ecosystem that you can go off and run on your accelerator. Now, you may have to tune it a little bit, but the reality is all of that data movement, all of the systems to enable all of that oneAPI ecosystem to run on the accelerator is now working for you. So it's achieving a lot for you. So as part of our commitment to openness, what we do is we give you a sample implementation. So we use the RISC-V process core, which is a standard open process design. You can go and take the RISC-V ISA, and you can go and implement it yourself, and you can find open source or commercial implementations of RISC-V. So you might think to yourself, well, RISC-V is a CPU, and I've got an accelerator. But it turns out a lot of people are thinking about RISC-V for a CPU, but a lot of people are actually thinking about RISC-V for their accelerator. So it's a bit strange, isn't it? Why would you want a CPU as the accelerator? The answer is that when you have an accelerator, you need some programmability on it. Even if you're using AI, I think that people end up shocked about how much programmability you need for AI, but you need some programmability for AI. And one of the reasons for that is that if you look at these AI models and other kinds of data-centric computing, you'll find that there's compute-bound operations, things like matrix multiplies, and bandwidth-bound operations. In AI, you'd have things like value and pooling and stuff. In HPC, you have the equivalence, right? But there is no point optimizing your bandwidth-bound operation using special compute instructions, because something will go any faster, because you're limited by the bandwidth. That's what bandwidth bound means. The limit of your performance is limited by the bandwidth to memory. So therefore, what you do is you use the RISC-V programmable core for all of the programmable parts of the accelerator. And there's a lot of people doing this because it helps you build up an ecosystem. And then what you do is you put in special custom accelerators for the things that are compute bound, that are worth optimizing, like matrix multipliers. So from our software point of view, we're going to put most of the work into the compiler work, so we're going to put into the RISC-V core being used as an accelerator. So the vision of the oneAPI construction kit is open standards driven by industry collaboration. And this really is industry collaboration. You can join the UXL Foundation or Kronos Foundation for the SYCL standard, and you can help drive this. You can make comments on it, you can add your own implementation, you can make changes. If your processor design needs different features, if your software design needs new features or new languages or something, you can come along and you take part in this, and you can drive that in a different direction. It also enables you to take advantage of a huge existing ecosystem. That's a big thing with processors. To be able to just suddenly run lots of software is a fantastic thing. Even if you have to optimize it a bit for your processor, just being able to run a lot of software day one is fantastic. That's why people use processor architectures like RISC-V. You can design your own CPU core, but RISC-V is managing that ecosystem. With oneAPI, we're building out a big ecosystem. The software ecosystem is being talked about in other talks in this presentation. This is about the hardware ecosystem, but we're building out this ecosystem where things work together, which means that you can just get much more working from your processor. And this is going to enable SYCL and oneAPI for your processor. And we have just migrated the oneAPI construction kit to the UXL Foundation. oneAPI construction kit started at Codeplay. The oneAPI itself started at Intel. We're now migrating that all into the UXL Foundation GitHub and converting it into a fully open project. It's still work in progress, but we've got the oneAPI construction kit across. We've got initial CI, the continuous integration testing set up, which means that anyone can add their own contributions, go through the testing systems. We're adding more testing systems. We test this because this is neutral to what processor architecture you've got. We actually test this on simulators, on CPU, is how it works. So this is a big step for us with the UXL Foundation because it's actually starting to really build out this hardware neutral oneAPI fully open source project that you can contribute to. Anyone can come along and contribute to. So we're really, really excited about this big step that we've made. Okay, how it works. We're going to get you to SYCL first, and then from SYCL we get you to the rest of oneAPI. SYCL is the toughest thing in many ways to bring to a new processor core because you have to get the compilers working, you have to get the data flow working, the scheduler working, there's all sorts of things you have to get working. Once you've got that, then the rest of things start working, all the libraries and things start working oneAPI. You may want to be able to do some optimizations, put in your own features, your own special secret sauce and stuff, but this is the step. So we build this up easily in stages. So we've given you stages to go through it. So when you want to start to build the oneAPI construction kit for your new processor architecture, so that you don't have to build a LLVM compiler and a runtime and parallelism and all sorts of testing systems all at once, we have an easy starting point, which is what we call sync click. So this is synchronous, so you don't need to deal with the parallelism, and click is like an OpenCL. So SYCL is kind of based on OpenCL. You don't have to use OpenCL, but we use OpenCL. So when people use OpenCL, it's quite helpful. So it's simple, and it allows you to get a simple synchronous runtime up and running, and then it's got a test suite for that. And that's starting, when you start to implement that, you start to get to work. Then we get you to asynchronous click. So async click is when you're starting to have to deal with the parallelism and things, and in terms of how long it should take you, this is just a few days to get some of the early work done, right? So once you do asynchronous click, then you're having to deal with the parallelism. Maybe it takes a little bit longer, a few days, but it doesn't take very long. Then we have the MUX API. So the MUX API is what we use that has all of the features to be able to compile for your architecture. We have an offline version of MUX, so you can use a more conventional compiler. You will need an LLVM compiler. By the time you get to MUX, you need an LLVM compiler for the programmable parts of your processor. So if you've got an accelerator processor with a RISC-V core for the programmable parts of the processor, then you're in luck because LLVM already exists for RISC-V, so you don't have to do that. But at this stage, we're not going to deal with the non-programmable parts of the processor, things like matrix multiply units. So for the programmable parts of the processor, you've got an LLVM. You've probably got some DNA, so you're going to have to be able to deal with the DNA now with MUX. With sync click, you're going to have to deal with it a bit. Async, you're going to have to deal with DMA happening asynchronously, and then with MUX, you're going to have the full features of DMA to be able to move data between the different processors. So we've got sample implementations for this using simulators. So that's what we're using in the CI testing. That's what you can use. You can use simulators, and that allows you to get this up and running early in the design stage of your processor without actually needing to run on real hardware. So we find that makes life a lot easier. You could use real hardware, but we use simulators for the early stages of the design. You get MUX up and running, and then the whole of the rest of the construction kit and SYCL starts working. It doesn't necessarily take a long time. You might want to spend a bit more time later on doing more optimizations, but it shouldn't be a huge amount of work, assuming that you have an LLVM compiler for the programmable parts of your processor. We found that in AI processors, which is very common, you do need to have a programmable part for all of the custom operations and bandwidth-bound operations, right? We're not going to force everything onto it. I know people worry about, but our programmable processor is not as fast at some operations as the custom processors, but that's okay because it's going to be doing bandwidth-bound stuff, so it doesn't make any difference. But it is important that you have that to be able to run the AI ecosystem. And then you can start to be able to put in some of the other components and build out all of oneAPI and integrate all of your own custom hardware in. We document all of this, so there's actual examples and explanations for if you've got this kind of hardware, do this. If you've got this kind of hardware, do this. I know some people tend to prefer to start with their custom hardware first and the programmable hardware later. Starting like this with the programmable hardware can seem just a little bit weird, but actually it makes sense because it takes longer to do some of this stuff. So it's better to start earlier on the programmable hardware, and there's a lot of software there that you're going to have to get running, and then it's much easier to plug in the optimizations for your custom hardware later. So the simple version of it is those early Click implementations really are just 5 basic APIs. It's like super simple, right? You're allocating memory on your processor. So you do need to have a memory allocator on your processor, but it's not that hard to be able to do because you need to be able to allocate memory on the accelerator and on the host and maybe on other different memory systems that you've got. And then you need to be able to load a kernel and run it on the device, and you need to be able to move data across, basically. You need your own LLVM compiler. It doesn't have to be like it probably won't be a full-featured LLVM compiler like a CPU compiler. It doesn't have to be an LLVM compiler that's going to run all of Linux or compile itself, because you're not going to be doing that on your accelerator. You're going to be doing simpler stuff, but you need to have an LLVM compiler that supports the features that your processor has. And then you can go through the optimization phase. So this makes a little bit more sense to people who are actually got some hardware. We provide this reference implementation based on a RISC-V processor. So hopefully this helps you understand how you would map this to your processor. So we've got a host CPU, which could be anything, but we support x86, ARM, and RISC-V host CPUs. You've got host memory for your host CPU, and then you've probably got some off-chip accelerator memory for your accelerator. Not everyone knows, but a lot of people do, and that's often separate. Like a discrete GPU, you've got it on your board. Sometimes it's the same, and you can share it. In which case, there's ways of allocating memory that's shared. And then you've got DMA to move the data between the different memory units. And then you've got some on-chip memory, which is likely to be much, much, much faster than the off-chip. So that's why we managed on-chip memory. On-chip memory is generally much, 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 much faster, but also much, 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 much slower. Smaller. On-chip memory is much, 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 much faster, but also much, 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 much smaller. Right. And then we have a programmable accelerator, which would be a RISC-V core, and then we have a SIMD unit, which is a RISC-V vector unit. Now, most people designing these processors will have some custom hardware there, like a matrix multiply unit or a convolution unit, or sometimes they do more special operations like AI operations and stuff. We don't have that in our reference implementation because we treat that as your special custom IP. You're going to add that afterwards, and we can help you show you how to do that. But this is about getting the programmable part of the software up and running. So you're going to be able to add all of that stuff. And I know that it's going to be faster at compute bound operations, but the RISC-V stuff gets up and running first. And the reason we have this SIMD unit is you can put very, very dense compute on your chip. So you can have a lot of operations in a SIMD unit in a small amount of space and a small amount of power, whereas a fully programmable accelerator like a RISC-V CPU is much larger, so you don't get as much performance per area. So that's why probably you want the SIMD unit to be really big on your chip and the programmable accelerator to be really small. And then we're going to map the kernels to a combination of the programmable accelerator, but most of the processing is going to happen on the SIMD unit. We have all of these different components, and you can go to our website, developer.codeplay.com construction kit, and you can see all of this documentation. The documentation is structured to allow you to design your own processor architecture. So you may come to this and say, well, I've got some of this, but I haven't got that. Right, so you might have a RISC-V core, but you haven't got a vector unit for some reason, or you've got some other unit instead. or you say, I've got a slightly different memory system or a slightly different DMA system from what you've described. That's okay. You read through the documentation, you'll find it will describe how to deal with all of those different issues. And all of these things are kind of optional components. So we have, for example, a vectorization component that will convert GPU-style scalar code to SIMD code. So this is a really common thing we see. If you look at GPU kernels, they're written in a scalar form. So it'll have float A equals float B plus float C, basically, right? That's the scalar, that's just one float. But actually they're executed across massive tensors where the A plus B plus C is actually being done across all of the components of the tensors. So that's why those SIMD vector units are going to do that much, much more efficiently than a CPU would. So you may have gone, no, I'm going to put in a SIMD unit that does that. The way that GPU code is written is, even though it says it's scalar, it's actually copied across all of the different lanes of the vector unit, which is why GPU is actually really a vector unit, if you look at it. So although the code looks like it's scalar, you're then saying replicating it across all the vector units of the GPU. So actually it's a vector unit. So if your LLVM compiler takes SIMD style code, where you don't say float A equals float B plus float C, but you say float 128 equals float 128 plus float 128, right? Where you're saying take 128 floats and add them across. Our vectorization component will actually do that transformation for you. So your LLVM backend can take in vector types at the back end. And that's how RISC-V works. The RISC-V vector extension works like that. LLVM works like that. So you can actually see that working. So you write GPU style code at the top, where it's scalar, and out comes SIMD instructions for your RISC-V processor. That may be useful to you, may not be useful to you, up to you, you get to choose. You'll look at the math libraries, which have quite strict precision requirements in SYCL. That's because this is used for scientific applications and engineering applications where precision is important. You may or may not want that precision depending on what your customers want, but we provide high precision math libraries. You can provide lower precision ones that are faster, but you can still then pass the test suite and be able to sell to customers who require higher precision. And we add APIs to integrate your own optimized libraries. So if you've got something working really fast, right, we're not going to force you to replace it with the SYCL version or the LLVM version or whatever it is. You can integrate it in. You plug it in. And so people are going to be using your integrated fast libraries where you've done all the optimization in the situations where they're going to work, and in the situations where they're not going to work, they're going to be able to fall back on the SYCL code, so everything will work on your processor. So this is what the components look like. We deal with a whole load of standards. You'll notice that we talk about OpenCL, Vulkan, Unified Runtime, which is actually part of the interfaces now within oneAPI. So it's not just oneAPI stuff, it's OpenCL, which a lot of people use, as well as oneAPI or with oneAPI. Vulkan Compute API is used by quite a lot of people, quite an interesting thing. So there's quite a lot of stuff you can do with the construction kit, not just oneAPI, but it's helpful that these things all work together. And then you've got the runtime and compiler, and then customer device, as in your device, and a host device, so that's the accelerator. And then you've got a whole load of utilities which you choose to use or not use, right? So we've got SPIR-V consumer. So SPIR-V is the standard intermediate representation that we use, and we've got something that converts from LLVM to SPIR-V, SPIR-V to LLVM. It's actually really useful. SPIR-V is another one of those things where people keep arguing against it and then discovering it's incredibly useful and they should have used it all along. It doesn't slow down your code. I know people say it does. It doesn't. It's just a way of enabling you to plug in two LLVM compilers, which is actually a really useful thing to do. We've got image library for supporting a whole load of image things which exist in SYCL, math library for high precision stuff, and then a whole load of compiler tech for handling vectorization, work item scheduling, and a reference pipeline so you can understand what's going on. And then all of these reference targets. So you could start from one of these reference targets and customize it. And then a whole load of testing that starts from small testing to large testing. So you can test small, simple stuff first. Okay. Does it work? Accelerator is a great startup company, and they said, oh, we'll try the oneAPI construction kit. They have this really interesting AI accelerator processor. You can let them up, designed for edge computing, and they're embracing open standards for programming. So they thought, oh, why don't we add this, the oneAPI website, when they talk about how it all worked for them. And it gives them this direct parallel programming with C++ on their hardware. And it's got some optimized libraries, so they add their own optimized libraries as well in order to make it work. And it's helpful for them going to customers because they can say now they support OpenCL and SYCL and a whole load of libraries as well as oneAPI and some of their own stuff. So they implemented Compute Mux to be able to do the memory allocation on their device. So there's some memory on their device. I can't see where it is, but anyway, it's memory on their device. And then they implemented the APIs to transfer data from host device, and they implemented the APIs to execute commands to run kernel codes on their device. So those are all things they have. And this is what they said. The integration with oneAPI construction kit was straightforward, make it quick and easy to bring the whole open standards oneAPI ecosystem to the Metis AI PU. So very successful for them. If you're interested in this, I recommend reading their case study because they talk about how they went through it and how easy it was for them. Really did work for them. The other thing I said I'd talk about was some of the research projects that we're working on. So we're working on the Cyclops and Aero projects. These are European projects involving lots of great companies across the different ecosystem and scientific organizations and universities. So we're delighted to be part of these consortiums, and these consortiums to help fund and prove out some of this work and enabling the oneAPI construction kit, funded by a combination of the European Union and the UK Research and Innovation. So if you want to follow up on this, we have SYCL.tech, talks all about SYCL, and we keep that up to date with all the latest things going on with SYCL. And you can visit the Codeplay developer portal, and it's also now on GitHub as well. But I strongly recommend the Codeplay developer portal. We have various different products there for different users. Like some people are software developers wanting to use oneAPI on NVIDIA and AMD GPUs, for example. You can download that. We're going to talk about that at this event. But the oneAPI construction kit is really designed to be well documented for people who are bringing oneAPI to new hardware. So you're going to see it talk about, if I have this bit of hardware, do this. If I have this bit, do this. And you'll see all the source code. It's open source, runs on simulators. You've got a reference, so you can try it out and really work out how it's going to work for you. So you can get oneAPI working, but you can also work out where you can integrate your own optimizations and add your own special features. And that's it.